So this note section is covering two topics. The first topic is dealing with organic halides, which means basically what happens when you have an organic compound, but then you have a halogen attached. So the halogens that are typically found are fluorine, which they call fluoro, chlorine, chloro, bromine, bromo, or iodine, iodo. So what you want to realize for these is just instead of like having one carbon as a methyl group, or two carbons as an ethyl group, you have a halogen, which I've highlighted our branches in green. You still do everything else the same. You still name the long chain. You just have to remember that this has a specific name. So if you look at this first one here, and I will say these notes will go pretty fast. So if I go too quickly, certainly pause the video, take your time, but just I don't want to wait for a long time since I'm talking to myself. So if you look here, we have 3 carbons with single bonds, which is a propane. And we have a chlorine, which we call a chloro, on the very first carbon. So the name is 1-chloropropane. If we look over here, it's almost the same, but we have a chlorine and a methyl group. So just remember, you want to do your alphabetical. Chloro is alphabetically before methyl. So that's why it's 1-chloro, 2-methylpropane. The next slide has rings attached. You want to remember when you do rings, you have to find like where the best place would be the number 1 carbon. For number 4, it's actually easier because there's no double bonds or anything. So obviously you want the number 1 carbon to be where these guys are. The one up here is a little trickier because we have a double bond, but we actually get slightly lower numbers if we start on this side of the double bond and go counterclockwise for it. So you still name the rings first. And then you add these on as branches or substituents. So this one, you get a 4-chloro, so 1, 2, 3, 4, so that's our chloro. Then we have a 3-iodo, and then you have to remember to tell people that it's a double bond, and you have to tell them it's a ring, so it's a 1-cyclopentene. And just remember this 1 is telling us where the double bond is. The one down here is a little simpler. We just have the ring. There's no double bond involved, which makes it nicer. So on the number 1 carbon, we have a chloro. We also have a methyl, and it is a cyclobutane because of all the single bonds for it. There's one slide that's not in your notes. We wanted you to know that halogenated organic compounds are a lot of times known as CFCs or chlorofluorocarbons. Chlorofluorocarbons are used to make insulation, refrigerants, but they do have an unfortunate ability to actually bind with oxygen that would be in the upper levels of the ozone or in the ozone layer and actually form ozone. And actually they've been shown to contribute to the hole in the ozone layer. They've been banned for the last 50 years, and the ozone hole is actually, in the last year, there's actually been research showing that it is healing. But there was they made these elements or these compounds to basically help people. And unbeknownst to them, they were actually causing problems with the ozone hole. So just kind of like, where would you see these? The last thing for this video are the functional groups. Like I said, some of them you'll have already seen. Like I said, we're going to just kind of show you what it is. I would pause the video so you have time to draw the diagrams. And then just kind of make sure you understand what do they look like and how do they behave. So the first one that you guys have probably all heard of before are alcohols or phenols. All it really means is that they have this hydroxyl group here. The one on the left is a generic version on every slide. So this R just means that like any carbon chain could be there. The pictures on the right are going to be like actual chemicals. So this is ethanol for it. We use it for a wide variety of things. It's used a lot in makeup and skincare. It's used as gas additives. Obviously, ethanol that is not denatured can be used to produce drinks. And then phenols, it's literally a benzene ring with a hydroxyl attached. If you've ever used chloroseptic spray and you look at the ingredients, like phenol is the only ingredient, the active ingredient. So those are your alcohols and phenols. The second functional group we're going to look at are ethers. Ethers are my personal favorite functional group. What you want to realize here is it's just an oxygen trapped kind of in the middle of a carbon chain. This particular one down here, this is called dimethyl ether. So you have a methyl group on the left, you have a methyl group on the right, so it's the dimethyl ether. Ethers were used as rudimentary anesthetics, also refrigerants, and they're pretty easy to make. Down here, this is a nice reaction where you just take two alcohols. The alcohol, actually, you pull out of water, it's a dehydration, and then you actually form an ether. This one has two ethyls, which is why it's called diethyl ether for it. The third functional group we're looking at are actually a pair of them. It's called aldehydes and ketones. Aldehydes are on an end, so you'll notice that they end with like the hydrogen here. Ketones are the same thing, but they're not on an end. Aldehydes are a little more reactive just because of that. And then on the right here, you can see an aldehyde where it is on the end, or a ketone where it's kind of stuck in the middle of it. Aldehydes and ketones, if you like smells that are like spicy, cinnamon, vanilla, anything like those kind of fall scents like apple pie or anything, then you probably like aldehydes and ketone smells, because those are the natural scents that they occur. Also, sex hormones are aldehydes and ketones as well. You can make these again pretty easily with just by alcohols. So again, a lot of organic chem, you can go in the lab and make these and make smells and stuff, and it's a pretty cool experiment. Because they have such strong scents, they're used in perfumes a lot as well. The next one we're going to look at is carboxylic acids, which you should probably remember from bio. Again, what you want to look at here is we have the hydroxyl group, the OH, and we have the double bonded oxygen. Over here, we have just two of them here for the specific, but you want to make sure you realize like this has to be all together for it to be a carboxylic acid group. And then this is just showing you, obviously, where do we see carboxylic acids the most, like organic structures, like citric acid, that kind of stuff, and then obviously in proteins as well. And the next slide here is just showing you again, you want to see you have that carboxylic acid here, and you can see it forming down into the different amino acids and then eventually into the proteins. The next one we're going to look at is esters. Esters are related to carboxylic acids, but what you want to notice here, you still have the double bonded oxygen, you still have the O here, but there's not just it's not on the end. It's again kind of trapped. So I always say ethers are trapped and esters are trapped. So what they want you to see here is what they're showing you is this is a carboxylic acid, the ethanoic acid. But if you want to be an ester, you have to see it's not on an end. So there has to be at least one carbon on either side of it. Esters have flowery smells, fresh smells. So if you like fruits or flower smells, then you like esters. Again, they're used a lot in soaps because they're the major component in fat, and they're also used in like perfumes and like makeup and stuff like that. And then again, we're just going to look at a little picture to show you. Sorry, my son's interrupting us. The next slide here is just showing you how fats are formed. So again, you have your alcohols, we have our carboxylic acids, and then you actually make the bond, and then you get into the esters for it. So we have two more functional groups that we have. The first one is an amine. It's a nitrogen group with three things bonded to it. Most commonly what happens over here on the right here is you have nitrogen bonded to the carbon chain, and then you have hydrogen, two hydrogens coming off. Again, you can have other things, but the most common is this. And then amines do not smell very good. If you think that they're the major component in like amino acids, then what if they break apart, like anything decaying is like smells like amines. So amines do not smell very good, but they are a part of every single amino acid that we have. And then our very last one that we have are amides. So again, you have this nitrogen thing here, but then you have this double bonded oxygen over here. So you have the double bonded oxygen right next to that nitrogen here. When you take an amine, you obviously can change it into an amide. Amides are when you actually start branching everything out into proteins. And then just an example down here, something common, this is Tylenol structure, and you can see you have the amide right there. So you want to know generally what they look like, what do they do, and kind of what their structure is.